Hey everyone, I'm Andre,
I'm Charles.
I'm Nathan.
And I'm Kunal.
and this is definitely not Bruno Mars, our CS228 final project. We'll be going over the motivation for our project, the ML objective, how do we formulate our project as an ML task, the augmentation choices that we made, our struggles and design choices, and lastly, results and analysis. Let's get started with motivation. And I'll be starting off with the TikTok clip. Okay, so that clip was Drake, Kendrick Lamar, and Kanye West singing an anime OST. And a lot of these deepfake videos were popping up on TikTok, and we were pretty inspired by them and wanted to create our own audio and video deepfake using methods we learned in class. And we wanted to one-up these videos because these videos only have audio deepfakes, but we wanted to create an entire AI-generated music video.
So our objective is to create a full data pipeline in which we get our source singer, Bruno Mars, to imitate the audio and the pose of our target singer, IU. To do this, we first must generate audio data, or do something known as voice conversion. To do this, we use something called a GAN, a generative adversarial network. More specifically, we use an architecture called mass cycle GAN, again explicitly meant for voice conversion with computational efficiency in mind. In our case, we took the architecture and made some tweaks here and there to increase performance. So when we toss in the audio from Bruno Mars and IU as spectrograms into our GAN, we should have an output in which we have Bruno Mars that sings along to IU's song. A neat little feature about this GAN is that intrinsically it's a cycle GAN, a type of GAN that not only generates audio of Bruno Mars to IU, or source to target, but also generates audio from IU to Bruno Mars, or target to source. This can be very useful in determining what data augmentations are useful and what modifications we can make to the architecture in order to improve it. As for our second part of our data pipeline, we need to now generate the video data. This is also known as post-conversion. Rather than using an architecture from online, we decided to just use an external GitHub. So what we did is we got a video of Bruno Mars dancing on YouTube from his official channel, and then we got a video of somebody doing a cover for IU's dance. The reason why we decided to use a cover is because a lot of IU's videos are heavily edited and have multiple people, which isn't really optimal for our model and training. So by using cover in Bruno Mars's video, we're able to get a decent representation of Bruno Mars dancing to that cover. Now, like I said before, we didn't really make that many improvements to the existing architecture of the GAN. Our main contribution is using augmentations to create a more robust model and generate better results. So why does this exactly improve the GAN? Well, for one thing, when we have more augments, we can generate more data. And if we have more data, you typically get a better model. Our second reason, which we thought would be kind of cool and interesting, is that IU and Bruno Mars are very distinct. Our singers are very distinct ends of the spectrum. Bruno Mars is a male singer that sings in English. IU is a female singer that sings in Korean. We thought by using augmentations, we can bridge the gap between these two different vocal registers and languages and get a better result.
Let's get into augmentation. Due to the time restrictions of this video, we ask that if you would like to take a closer look at the spectrograms or plots, we ask you to pause. And if you want a deeper dive into what we're actually doing and more details on the analysis, we ask that you look at the report. Next slide. So we'll be going over time stretch, pitch shift, white noise, harmonic distortion, frequency mask, time stretch plus pitch shift, and time stretch plus frequency mask. So time stretch. Time stretch stretches the time of the stretches the time of the audio. It speeds up or slows down the audio without changing the pitch. We introduced this augmentation to increase the amount of data we have on each singer and what they sound like at different tempos and different speeds. This is particularly important because IU sings a lot of ballad songs, which are a lot slower than Bruno Mars's more upbeat, faster paced songs. Here's an example of the the signals to keep track of. Please make note that all the plots that we use from here on out use extremely large scalars to show visual differences, but our code uses more reasonable scalars. So in this image, we have a speed up factor of 2, as well as a slowdown factor of 0.5. Applying these augmentations, it's clear that slowing down increases the height of a lot of the peaks in the signal, and a lot of the peaks are in close proximity, which make them look fuzzier, louder, and less sharp, and vice versa for speeding up. The spectrograms here, we can't really see a visible difference besides the varying time durations. Pitch shift transforms the pitch to keep the sound, to make the sound different, but the speed the same. We introduced this augmentation to get more data on how the singers would sound if they spoke or sang in different musical keys. We have IU singing in a different register than Bruno Mars, so we don't have any data of what IU would sound like if she used a lower singing voice, for example. Here's an example of the pitch shift. We used, in this example, 12 semitones up and 12 semitones down, which is equivalent to an octave up and an octave down. Much like time stretch, the visual differences we see here are very similar. We see that pitching up a sample increases the height of a lot of the peaks, again, which make them look fuzzy, louder, and less sharp. Here are the spectrograms. These are interesting because speeding or pitch shifting up makes the original spectrogram stretched vertically, while pitching down will compress the spectrogram. And we see a black bar across the top of the shift down, primarily because most spectrograms actually only look at the melodies or the treble of the audio instead of the bass. So shifting down, we're looking at frequencies that don't exist on the spectrogram. White noise adds random values from a Gaussian distribution to the signal. Typically in image data augmentation, this would apply a blur effect, and we wanted to apply that same effect to audio instead. So here's an example. We used intensity 0.2 and 2.0, and as you can see, the greater the intensity, the greater the range of amplitudes get masked out or drowned out. Here are the MEL spectrograms. Again, we see how the greater the intensity, or adding white noise at all removes all silent segments of the video or of the audio, and adding higher intensity white noise will reduce the difference in the loud and soft sounds. So that's why we see the decibel range actually decrease as the higher intensities. We also have harmonic distortion, which is just 5 consecutive sinusoidal transformations. Here, the original is clipped from -1 to 1, but we see that when we apply harmonic distortion, the range is changed, and most of the peaks converge at -6 or -0.6 or 0.6. Here's the spectrogram. We see that there's a lot harsher contrast between the light and the dark, so that suggests that there's not a lot of in-between volumes, and we see that there's a lot of streaking as opposed to the broken up segments in the original sample. We also used a frequency mask, but in our case, we more specifically used a MEL band mask, which is a MEL is just a different measure of pitch, but the difference between two MELs is indicative of how different two frequencies sound rather than the absolute difference of their frequencies. So this encourages the model to look more at general patterns and frequency ranges that are more audible and distinct to the listener.
Okay, let's get into our struggles and design choices. And let me tell you, we had a lot of struggles in this project. First, we're using the Masscan VC. We asked the TA if we can use an existing implementation of Masscan VC, and we did use an existing implementation, but it didn't work out of the box. We had to make so many changes to the files to make it work for our own training data and have the ability to apply the data augmentations that we wanted to. And we spent days trying to get the model to work, testing individual components, getting rid of components that weren't needed or were broken. We were also making our own data preprocessing pipeline for the model and implementing our own logging system. Next, we were dealing with long training times. The original paper trained on 500,000 iterations. This is about 2.5 days of training time. Well, we have 8 augmentation policies, and we have 2 types of voice conversion, male to female and female to male. So that comes out to 40 days of training. We have to consider my electricity bill, number 1, and number 2, the room temperature while training, because these GPUs get really hot and I can't sleep. So we also had to consider the project due date. So instead of training for 40 days, we decided to train sparingly and only choose the best augments to train further.
Another problem that we had is that we needed to find a way to measure the effectiveness of augments. The paper used MCD, which stands for milliceptual distance. Basically, you can think of it as Euclidean distance. The larger the value, the less similar it is, and vice versa. It turns out that we cannot use MCD on our own vocal data because we don't have parallel voice examples, which is when target and source voices are speaking the same sentence. We decided to train both the original dataset as well as the augmented sets and use the three best augmentations to train on the singer's dataset. We decided to pre-process the data in order to reduce applying augmentation during training. This reduces the runtime mainly because we don't have to perform a deep copy of the tensors every time we augment the data. Augmenting the data also is very costly during training, so it's good that we augment it beforehand. A common issue that we all had during development is that the libraries are outdated. For example, a vocoder was using an older version of Labrosa. There were also too many dependency issues, such as the vocal separation library splitter, which required a certain Python version, but it was not mentioned anywhere on documentation. The results weren't that good either, so we just downloaded the raw vocal file from YouTube. Google Colab also does not let us train for a very long time. It often kicked us offline because we were idle. Also, the paper's implementation used TensorFlow 1, and Google Colab only supports TensorFlow 2, so we spent a lot of time looking for a workaround.
Okay, let's get into our results. So we trained on the original dataset from the original paper, which was the VCC 2018 dataset. And we wanted to do this because we wanted to use our objective evaluation, the VCD, or sorry, the MCD. And if you look at the graph, higher numbers on the y-axis means it's worse, performing worse. And we'll see that some of the augmentations actually do improve on the no augmentations from the original model. And also we notice that female to male conversions have a tougher time than male to female conversions. And once we got those results and we trained for our own data sets, we asked 32 people to fill out a survey to evaluate our generated samples. And we used the survey results to calculate mean opinion score. Mean opinion score is when we ask the participants to rate our samples from 1 to 5, 1 being really bad and 5 being really good. And we get the mean of those, and that's the score. For our survey, we wanted to evaluate on 2 aspects. Number 1, the quality of the generated audio sample, which is what I just talked about. And number 2, the ability to generate the other voice. For this one, we asked them, does the sample sound like IU or does it sound like Bruno Mars? And we expect there to be an even distribution of Bruno Mars and IU. And in the survey results, for the augmentation ability, we actually got pretty poor results. So IU was the only one that was able to be heard, even if we were converting to Bruno Mars. So this is kind of similar to the MCD results, which showed that female to male conversions struggled significantly more. And this is for the average rating of quality of samples. We also didn't get too good results here. We got mostly poor or fair. So the main takeaway is that the mass scan needs a lot of time to fully converge in order to generate good quality samples and a lot of computation power. So let's get into the video and audio results. And we will link this Notion page in the report or even in the submission. So this is the first data set results.
And said he would go and consult his master.
And said he would go and consult his master. And said he would go and consult his master.
And the source and target stays the same, so I'll just play the generated samples.
And said he would go and consult his master. And said he would go and consult his master.
So for this one, it's kind of like a mix. You can't really tell if it's female or male. And here's the next one.
And said he would go and consult his master.
Oh, sorry, target.
Said he would go and consult his master.
Would go and consult his master. And said he would go and consult his master.
And said he would go and consult his master.
And said he would go and consult his master.
And the last one.
And said he
So they're almost like demonic. And we built a visualization expecting our audio samples to be good. So we just wanted to highlight that for a quick second. Cool. And we want to highlight this. This is all computer generated, and the waveforms are actually dynamic to the audio. And this is a generated sample with our visualization. And if you're wondering why you can't hear it, it's because when we convert it, the amplitudes for some reason aren't loud, and it's reflected in the video. Like the amplitudes of these waveforms are pretty small. And that was one of the biggest complaints during the survey. Lastly, we have the last piece of our music video is the dancing. And so here's the original. Cool. And this is the target, or sorry, this is the generated sample. Yeah, so it looks pretty good. I just want to highlight that one of our members, Nathan, stayed up until 7 a.m. for 5 days straight to get this to work. And we thought it wasn't going to work, but he got it last minute. So big congrats to him. And that concludes our presentation. Please read our report for more information. And thank you. Bye.